Hello everyone. Before we get to this lesson, let's try the warm-up. What's the missing number in each case? Hopefully you got the first two no problem. You might have had some trouble with the last one because you might have been thinking, well, 5 minus something gets me 8. That's bigger than 5. That doesn't make any sense. But just remember, if you subtract a negative, that simplifies to adding. So 5 minus negative 3 is the same as 5 plus 3, which is 8. So why do I bring this up? Well, I'm not just testing your guessing abilities. I'm actually getting you to think about how do you figure out the missing number. Well, you might just intuitively have known that 7 plus 3 is 10, but you also know that you can work backwards. 10 minus 7 is 3, and you can find the missing number that way. And that leads us into this lesson's discussion. This is an introduction to algebra. Now, algebra is what we use to solve problems like we did in the warm-up. However, usually the problems are a little more complicated or harder, but the thinking is the same. We're basically just working backwards to figure out what the missing number is. So we're still in Spiral 1, but now we're on the next topic, which is all about algebra, and this is the first lesson in our topic. Write today's date in your notes, and away we go. Let's start with some terminology. When we're dealing with algebra, I'll use the words term and expression, and technically they mean different things. So terms are the basic building blocks of algebraic expressions. So here I have a little image for you. Here we have a term, and a term. There's 3 terms in this expression. So the whole thing is the expression. Each part is a term. Now terms are separated by addition or subtraction. Now I have 2 blue blocks and 3 red blocks plus 6. And I can rewrite that with numbers like this. Let's say B represents the number of blue blocks, R represents the number of red blocks, and our expression, we have 2 blue plus 3 red plus 6. So I can write my expression like this. So you're going to see this type of expression a lot, where you have a mixture of numbers with letters. Now there's some more terminology within an expression and within terms. And it's this. So the entire statement is called an expression. But the letters are called variables. So each letter is a variable. So what that means is that it's a number, but the value can vary or change. It's a changeable number. And that's in contrast to a number like this. The number 6 is a constant. This number has a constant value. It is unchanging. So you have variables and you have constants. Now, here I have 2b. That just means that I have 2 of whatever these variables represent. That number in front of the variable is called a coefficient. So, expressions are made up of individual terms. A term can be a constant, or it can contain a variable. If the term contains a variable, the number in front is the coefficient. And just remember, the reason why we have terminology and we need to know the definitions of these words is so that you can understand what I'm talking about when I use those words, and also so that people will understand you when you're talking about these mathematical ideas. So let's look at 3 examples here. Here's an expression, here's another expression, and here's a third expression. How many terms does each expression have? Well, for the first one, we have 1, 2, 3 terms. Remember, terms are separated by addition or subtraction. So here's my subtraction. It separates out the 3 terms. The next one, how many terms does this expression have? Just 2. Some people might be tempted to think that this is somehow 2 terms here because you've got an exponent there, but it's not separated by addition or subtraction. So this is 1 term, this is another one. And the last expression has only 1 term. So it's good if you can count how many terms there are, but the reason I'm bringing this up here is because there's more terminology. If an expression has 3 terms, we call that a trinomial. If it has 2 terms, we call that a binomial. If it has 1 term, we call it a monomial. So look at the prefixes, tri, bi, and mono. Anytime you see those prefixes, they mean 3, 2, and 1. Nomial comes from a Greek word that means number. So trinomial just means there's 3 numbers. So we have 1, 2, 3. Same with binomial or monomial. You might be familiar with the prefixes tri and bi from tricycle and bicycle, 3 wheels, 2 wheels. It's the same prefix, so that's kind of how you can remember those. So the reason I bring this up is just so that if I say trinomial, you know that I'm talking about an expression with 3 terms. If I say binomial, you know I'm talking about an expression with 2 terms, etc. Now, most people ask me at this point, what if there's 4 terms? What if there's 5 terms? Well, just in general, algebraic expressions are called polynomials. So the prefix poly just means many. So basically, if you've got 4 or more terms in your expression, you just call it a 4-term polynomial or a 5-term polynomial. That just simplifies it for you. So an algebraic expression like these can also be called polynomials, or more specifically, a trinomial or a binomial or a monomial. So again, this is all just terminology, so you get an idea of what mathematicians are talking about. Another phrase that I will use a lot is like terms. So like terms are terms that have the same variable and the same exponent on that variable. So here I have some options, and I'd like you to look at each of them and see if each option has like terms or not like terms. So if we look at 2x and negative 3x squared, are these like terms? Well, they have the same variable. They both have x, but they do not have the same exponent on the x. If you don't see an exponent, it just means the exponent is 1. So this x has an exponent of 1. This x has an exponent of 2. So just because you have the same variable doesn't mean they're like terms because they have a different exponent. So these are not like terms. The next options, 4y squared and 8y squared. Are those like terms? Yes, they are. They both have the same variable, y, and the same exponent on the variable, 2. So these are like terms. What about the next one? 2x and negative 3x. Some people say these are not like terms because one's positive and one's negative. But remember, that has nothing to do with it. Do they have the same variable? Yes, both x. Do they have the same exponent on the variable? Yes, 1 and 1. So these are like terms. What about this? Negative 4y and negative 4x. Are those like terms? A lot of people will say yes, but they're wrong because they don't have the same variable. The reason people get tricked here is because they both have minus 4, minus 4. So they think, well, that's the same, so these are like terms. But no, so these are not like terms. So you need to be able to figure out what are like terms and what are not like terms when we start to actually do algebra. For right now, I'm just going to move on to some more terminology. There's something called a degree. So the degree tells us the highest exponent value. And there's two ways you can think about degree. The first way is to think of the degree of a term. The second way is to think of the degree of the entire polynomial. And to determine the degree of a term, you have to add up the exponents in the term. To find the degree of a polynomial, you have to pick the term with the highest degree. So this bears having some examples so that you can see what I'm talking about. So here's some individual terms. And I want to know the degree of each term. I'll have to add up the exponents. In this term, the exponents are 2 and 2. So that's a total of 4. So this has a degree of 4. The next one, 17.2ab. Well, I don't see any exponents. Does that mean this has a degree of 0? No. Remember, if you look at the variable and you don't see an exponent, that means the exponent is 1. So there's an exponent of 1 on this variable and an exponent of 1 on this variable. So total, we have a degree of 2. This last term has no variable, which means there is no exponent on the variable. That means we have a degree of 0 for this one. But now let's look at this polynomial. How many terms does this polynomial have? 1, 2, 3, 4. This is a 4-term polynomial. But I want to know what's the degree of this polynomial. In order to know that, I have to find the degree of each individual term first, and then whichever degree is the highest, that's the degree of the polynomial. So if we look at the first term, what's the degree? Add the exponents, 2 and 2, so this has a degree of 4. The next term, the exponents are 5 and 2. Don't forget the 1. You don't see the exponent on this variable, it's a 1. So 1 plus 2 is 3 plus 5 is 8. This term has a degree of 8. The next term has a degree of 3. That's the only exponent on the variable. This last term has no variable. This has a degree of 0. So which term has the highest degree? Well, it's this one, a degree of 8, which means this whole polynomial has a degree of 8. So you can find the degree of an individual term. You can find the degree of an entire polynomial. The reason we're looking at this is so that if I talk about a 4th degree polynomial, you'll know what I mean. And if you say the degree of a polynomial, another mathematician would know what you're talking about. So let's finish off the lesson with a few examples. Here's the first one. Jimmy is 5 years less than twice Helga's age. You might think, well, that makes no sense, but if we go through this slowly, we can piece together what it's talking about. We're going to write an expression for Jimmy's age, and then we're going to figure out how old Jimmy is. So before we write an expression for Jimmy's age, I want to show you this here. This is a reminder to define your variables. What do I mean by that? Well, first off, the variable is a number for which we don't know the value. So since we're trying to find Jimmy's age, we have to look at the clues. Well, Jimmy's age is given as a relationship to Helga's age, but we're not told what Helga's age is. So we can say Helga's age is our variable. So I'm going to say Let H represent Helga's age. And now I can write an expression for Jimmy's age. Jimmy is 5 years less than, okay, let's stop there for a second. 5 years less than something. Well, let's start with the something. The something is twice Helga's age. Okay, how do I write that? Twice Helga's age. Well, twice means 2 times. So this is 2 times Helga's age. We can write that as 2H. So his age is 5 years less than 2H. So less than means you're subtracting. If it's 5 less than, it means we're subtracting 5. So we take that 2H and we subtract 5. So my full expression for Jimmy's age is 2H minus 5. Okay, if Helga is 13, how old is Jimmy? And I say over here, substitute and evaluate. So these are some words that we can use to explain what we're doing. Substitute just means replace. So what am I replacing? Well, in my expression, H is a variable. It's a number with an unknown value. But now I'm being told Helga is 13. So I'm going to replace H with 13. I'm going to substitute H with 13. So my expression becomes 2 times 13 minus 5. And we can just keep doing the math. 2 times 13 is 26, and 26 minus 5 is 21. So we can say, therefore, Jimmy is 21. In this last example, we're going to do some practice substituting and evaluating. Let A equal -3 and B equal 7. Evaluate this expression. So this expression is -2a squared plus 5b. Okay, remember, substitute just means replace. Evaluate means find the value. And we've done that before by following the rules of BEDMAS. So let's start with our expression, -2a squared plus 5b. A is replaced with -3, and b is replaced with 7. So that makes my expression -2 times -3 squared plus 5 times 7. And remember to follow the rules for BEDMAS. Now that we've substituted, we can evaluate. Exponent comes before we do multiplication. So the exponent means we multiply the base by itself 2 times. Our base is -3. So if I wrote this in expanded form, it would be -2 times -3 times -3 plus 5 times 7. So now I can do all the multiplication. Now I have 2 terms that I can add together, and I get my final answer. So in this lesson, there was a lot of terminology about algebra, and hopefully you don't get bogged down in trying to memorize all these different terms. Hopefully, the more you use them, the more you're exposed to them, the more you will remember their meaning. And really, the most important thing that we're going for is that you can actually recognize what to do when you're working with an algebraic expression. Like we did here, we need to be able to substitute and evaluate. So if you have any questions about anything from this lesson, please let me know and I'll do my best to help. Otherwise, you can move on to the practice questions.